Hello everyone, welcome to the channel. In this video we are going to solve the exercise questions of Unit 3 Structure of Atom. We can see this chapter in our subject Chemistry and it is in class 11th. Now let us take the first question. So here we have the first question, that is calculate the number of electrons which will together weigh 1 gram. Means in 1 gram how many number of electrons are present. So we know that if it is one electron mass is 9.10 multiplied with 10 power minus 31 kg. So this is the mass of one electron or mass of an electron. Now how many number of electrons will be there? Let it be x number of electrons are there in 1 gram. We can convert this kg in grams. So it will be 9.10 multiplied with 10 power minus 28 gram. Now just cross multiply the values. It will be 1 multiplied with 1, that is x equal to x multiplied with 9.10 multiplied with 10 power minus 28 gram. Then x will be equal to 1 upon 9.10 multiplied with 10 power minus 28. Now if I solve this one, I will get the value as 1.098 multiplied with 10 power 27. So these many number of electrons will be present in 1 gram of it. Now we have second part also. In this question it is given calculate the mass and charge for 1 mole of electron. Let us solve this question. We have the point of relation that if it is 1 mole of electron, this 1 mole of electron will be having 6.022 multiplied with 10 power 23 number of electrons, and this will be equal to the mass of electron, that is 9.10 into 10 power minus 31 kg. So 1 mole of electron will be having the mass, that will be 9.10 into 10 power minus 31 kg. This is the mass, this mass is mass of electron. And when I talk about charge of electron, the charge of electron is 1.6 into 10 power minus 19 coulomb. This one is a charge of electron, but we have to find that if it is 1 mole of electron, what will be the mass, and if it is 1 mole of electron, what will be the charge. So we can see here, if 1 mole of electron contain this many number of electrons, so we can see mass of one electron mass is given as 9.10 into 10 power minus 31 kg. Then these many number of electrons, 10 power 23, 6.022 into 10 power 23 number of electrons are there containing having mass x kg. Now we have to cross multiply. It will be x, that is 6.022 into 10 power 23 multiply with 9.10 multiply with 10 power minus 31 kg. Now if I solve this one, I will be getting as 5.48 multiply with 10 power minus 7 kg. So this will be the mass for 1 mole of electron. Similarly we can have we know that 1 mole of electron having this many number of electrons, so 6.022 into 10 power 23 number of electrons are there having dash charge, x charge is there, and for one electron, the charge is 1.6 into 10 power minus 19 coulomb. Cross multiply the things, it will be x will be equal to 6.022 into 10 power 23 multiply with 1.6 multiply with 10 power minus 19 coulomb. If I multiply these two values, I will be getting as 96368 coulomb. So this will be the charge of for 1 mole of electron, and this will be the what I'll say, it is the mass for 1 mole of electron. So in this way we will solve this question. Let us move on to our next question, that is question number 2. In question number 2 we can see here it is having some parts. Let us take the first part. In the first part it is said that calculate the total number of electrons. We have to calculate the number of electrons present in 1 mole of methane. Here it is given 1 mole of methane. Now when I see here we have methane molecule. In this single molecule of methane will be having 10 electrons. Carbon is having 6 and each hydrogen will be having 1, so it will be 10 electrons. So we want to find out number of electrons in 1 mole of methane. So if it is 1 mole of methane, 1 mole of methane will be having how many electrons? So we know that 1 mole of methane having 6.022 into 10 power 23 number of methane molecules, and we have already calculated that for one methane molecule it is having 10 electrons. So for 6.022 into 10 power 23 number of methane molecules will be having x electrons. Cross multiply, it will be 6.022 into 10 power 23 multiply with 10. If I solve this one, it will be 6.023 into 10 power 24. This will be the number of electrons that is present in 1 mole of methane. Let us have now the second question. In this one we will see that we have to find a total mass of neutron in 7 milligram. We are taking 7 milligram of carbon 6614, and it is given that mass of neutron is given as 1.675 into 10 power minus 27 kg. So here we will see that total number of carbon atoms. First of all we will find the total number of carbon atom. So it will be, we are trying to find the total number of carbon atoms. It will be weight upon atomic weight multiply with 6.022 into 10 power 23. So the given weight is 7 milligram, so it will be 7 multiplied with 10 power minus 3, that is in grams, upon carbon 14, that is 14 gram, the atomic weight, the given weight, multiply with 6.022 into 10 power 23. Now if I solve, it will be 3.011 into 10 power 20. So this will be the number of carbon atoms. The second part, here we have found number of carbon atom. The second part which is here, that is first one we will see number of carbon atom we have found. Now we can here take the first part. Each atom of carbon means each atom of carbon C614 will be having 8 neutrons. Now we need to find out total number of neutrons. So it will be total neutrons will be these many carbons are there, so it will be multiplied with 8. So 3.011 into 10 power 20 multiplied with 8, it will be 2.4088 multiplied with 10 power 21. So this many number of neutrons will be present. B part, we have to find the mass of total neutrons. So these many neutrons are there. So if you want to find out the mass of neutrons, I have to take the how many neutrons are there, that is 2.4088 into 10 power 21, that is multiplied with the mass of a neutron is given 1.675 into 10 power minus 27 kg. If I solve this one, it will be 4.0347 into 10 power minus 6 kg. So this will be the mass of neutron, the total mass of the neutron. Here in this question we have third part also. Let us solve this one. Here they are saying that find the total number we have to find, and total mass of proton we have to find the mass also, and the total mass for case of proton. In 34 milligram of ammonia, it is given that 34 milligram of ammonia we have to take the sample at STP, standard temperature and pressure condition, and let us first of all find out how many number of ammonia molecules are there. So we can see we can apply the mole concept and we can easily handle this one, finding the number of ammonia molecules. So it will be atomic mass, which is given as 34 into 10 power minus 3 in grams. I have done the milligram converted into grams, divided by the atomic mass, that is 17 for ammonia, multiply with the Avogadro number, that is 6.022 into 10 power 23. If I solve this one, it will be 1.2046 into 10 power 21. So these many number of ammonia molecules are there. Now we are lacking with the space in this page, so I am solving this part here. Let it be A part. We need to find out the total number of protons. So total number of protons we can find in this way. So we have got the point that how many number of ammonia molecules are there. So one we need to find out the protons. So each molecule of ammonia contain 10 protons, 7 protons from nitrogen and 3 protons from hydrogen. So 10 protons are there in one molecule. In one ammonia molecule, 10 protons are there. So we have how many ammonia molecules? We have these many number of ammonia molecules are there, 1.2046 into 10 power 21 number of ammonia molecules are there. It will be having x protons. Cross multiply the things, it will be 1.2046 into 10 power 22 number of protons will be present in this case. Similarly, we need to find out the B part, that is the mass of total protons. So we can see here that if there are this many protons are there, so I will take this number of protons 1.2046 multiply with 10 power 22, and now I need to multiply with the mass of one proton, which is 1.672 into 10 power minus 24 gram. If I solve this one, if I multiply this one, it will be 0.0201 gram. So in this way we will solve this question. Let us move on to our next question, that is question number 3. Question number 3 is how many neutrons and protons are there in the following nuclei. So one by one we will take the arrangement. So here element is there, element is carbon, say 6 13, then we have oxygen 8 16, then we have magnesium 12 24, Then we have iron, that is 56, that is 26, 56, and we have strontium, that is 38 and 88. So the down one we call as atomic numbers, the superscript which we call as mass number. So here we need to find out the electrons here. So electrons are 6 electrons, here it will be 8 electrons, here it will be 12, here it will be 26, here it will be 38. We can see the atomic numbers. The atom is neutral atom, so if the atom is neutral, the number of electrons will be same. Now number of protons will be 6, 8, 12, 26 and 38. This many number of protons are there. What about neutrons? So neutrons will be, we will see 13 minus 6. We know that your mass number is equal to number of protons plus number of neutrons. We know the mass number, we know the number of protons, so we can get the number of neutron as mass number minus number of protons. So it is 13 minus 6, 13 minus 6 it will be 7, 16 minus 8 that is 8, 24 minus 12 that is 12, 56 minus 26 that is 30, and 88 minus 38 that is 50. So these many number of neutrons are there, these many protons are there in each species of the category which is given here. Let us move on to the next question, that is question number 4. Write down the complete symbol for the atom with the given atomic number Z and atomic mass A. So first case is there where Z value is 17 and A value is 35. Here Z is atomic number. Atomic number 17 is for chlorine. So it will be chlorine 17, mass number is 35. So in this way we'll represent. Second one we have Z value is 92 and A value is 233. So atomic number 92 is for uranium and its symbol is capital U. So it will be U92 and mass number is 233. Third one we have Z value is 4 and A value is 9. When atomic number is 4, we call as beryllium. Beryllium is there, so symbol is Be. So Be 4 and mass number is 9. So this is the representation for symbolic representation for the different atoms as per the atomic number and mass number which is given in the question. We can move to next question now. Question number 5. Question number 5 is yellow light is emitted from a sodium lamp who has a wavelength of 580 nanometer. Wavelength is lambda. Calculate the frequency, that is nu, wave number nu bar of the yellow light. So let us solve it down. We know that wave number nu bar is reciprocal of the wavelength, so it is 1 upon lambda. So put the values. 1 upon lambda value is given 580 nanometer, so I will convert into meter. 580 multiply with 10 power minus 9, it will be in meters. Now if I divide it down, I will be getting as 1.724 multiply with 10 power 6 meter inverse. So that will be the wave number. Similarly, we can find the frequency. We know that nu is equal to c upon lambda. C is the speed of light, that is 3 into 10 power 8 meter per second. Lambda is already given 580 multiply with 10 power minus 9 meter. Now if I solve this one, it will be 5.172 into 10 power 14 hertz or cycle per second. That will be the frequency. So in this way we will solve this question. We can have to the next question now, that is question number 6. In this question number 6, it is said that find the energy of each photon. We need to find out energy of each photon which correspond to the light of frequency. Nu is given 3 into 10 power 15 hertz. This is 3 multiplied with 10 power 15 hertz, that is the frequency which is given. And here we have second part, which is having a wavelength lambda which is 0.50 angstrom. Let us solve this one. We know that energy is equal to photon of energy, that is packet of energy. uh, E equal to h nu is given, the relationship. Here h is Planck constant, so 6.62 into 10 power minus 34 joule second, multiply with nu is given, frequency 3 into 10 power 15 hertz. Solve this one, multiply this one, it will be 1.9878, multiply with 10 power minus 18 joule. Energy will be in joule, so it will be the first case. Similarly, we can go for the second one. Here we can see we know that E equal to h nu is given. Now E equal to h is Planck constant, nu is c upon lambda. Now h is given 6.62 into 10 power minus 34 joule second, multiply with c, that is 3 into 10 power 8 meter per second, divided by lambda is in angstrom, so 0.50 into 10 power minus 10 meter. So I have converted that angstrom into meter. Now finally, if I solve these values, it will be 3.975 into 10 power minus 15 joule. So this will be the case 2 in this question. So in this way we will utilize this particular formula and cover up this question. Moving to question number 7. In question number 7 we can see we have to calculate the wavelength, frequency and wave number, that is nu bar, and that is for a light whose period is 2 into 10 power minus 10 second. So here time period they have given. So we know that frequency is equal to 1 upon t, reciprocal of time period. So frequency is reciprocal of t, so it will be, we can calculate the frequency, so 1 upon 2 into 10 power minus 10 second. So if I solve this one, it will be 5 into 10 power 9 hertz. So we get this value of frequency now. Now we can have another relationship, nu is equal to c upon lambda. So now lambda will be what? Lambda will be c upon nu. So c value is known, c, that is 3 into 10 power 8 10 power 8 meter per second, divided by nu, that is already we have found 5 multiplied with 10 power 9 hertz. If I solve this one, it will be 0.06 meter. So we have got lambda also, we have got frequency also. So similarly we can have the calculation for nu bar, that is wave number. Wave number is the reciprocal of wavelength, so it will be 1 upon 0.06 meter. If I solve this one, it will be 6, it will be 100 upon 6 meter. If I divide, I will get some value, that will be the answer for a meter inverse. So 100 upon 6, it will be nearby, it will be nearby 16.66 meter inverse, that will be the wave number. Move out to question number 8 now. Question number 8 is, what is the number of photons? What is the number of photons of light with a wavelength 4000 picometer that provide 1 joule of energy? So we know that E is equal to nh nu. N represent n number of photon particles, so then it will be n h nu is c upon lambda. E is energy, so energy which is given here is 1 joule. N is not given. What is the number of photons? Multiply with Planck constant 6.62 into 10 power minus 34 joule second, multiply with c, that is 3 into 10 power 8 meter per second, divided by lambda. Lambda is 4000 picometer, so I will convert into meter. 4000 multiplied with 10 power minus 12 meter. So I need to find out only the n value, so I can get it down here. N will be equal to 4000 into 10 power minus 12 meter divided by 6.62 into 10 power minus 34 joule second, multiply with 3 into 10 power 8 meter per second. If I solve this one, I will get some value, that is 2.012 into 10 power 16 number of photons, that is quantas means photons, that is a packet of energy. So this many number of photons will be present here. Now we have reached to question number 9. In question number 9 is given that a photon, we are talking about photon, that is packet of energy, that is having wavelength, that is 4 into 10 power minus 7 meter, that strikes a metal surface, the work function of the metal being 2.13 electron volt. So here this is the metal function, so the work function is, let it be E naught 2.13 electron volt. calculate the Calculate the energy of photon in electron volt. And the second one is the kinetic energy of emitted photoelectron. And the third one is the velocity of the photoelectron, velocity of photoelectron. So these things we have to calculate, that is the question mark. So let us solve this one. We know that E is equal to, energy of photon is E equal to h nu, let it be one photon, so h into c upon lambda, nu is c upon lambda. So we can see here h is 6.62 into 10 power minus 34 joule second, c is 3 into 10 power 8 meter per second, divided by lambda value is given in meters, 4 into 10 power minus 7 meter. Now if I solve this one, it will be 4.9695 95 into 10 power minus 19 joule. So we have got the energy in joules. We can calculate in electron volt. We can just divide 4.9695 into 10 power minus 19 joule divided by 1.6 into 10 power minus 19. So it will be in electron volt. If I solve this one, it will be 3.1 electron volt. So we have got the first part, that is the energy of photon in electron volt, that is we are getting 3.1 electron volt. Now we can go for the second case, that is kinetic energy. Second case is given that kinetic energy is what, the energy minus the work function. So here we have got 3.1 electron volt minus the E naught value, that is the work function of metal, is given as 2.13 electron volt. If I subtract, it will be 0.97 electron volt. Third is we need to find out the velocity. So kinetic energy, we know the formula, kinetic energy is equal to half mv square. So this kinetic energy is in electron with volt is given 0.97 electron volt. So 1 electron volt is having how many joules? So it will be 1.6 into 10 power minus 19 joules. So I have converted the answer in joules, equal to half. Mass of electron is, that is 9.10 into 10 power minus 31 kg. Now velocity v square. So finally v square will be equal to 2 multiply with 0.97 multiply with 1.6 into 10 power minus 19 divided by 9.10 into 10 power minus 31 kg. If I solve this one, it will be now finally we are getting that v square will be this much, then v will be what? So it will be, after solving this one, we will get 5.84 into 10 power 5 meter per second. So that will be the result in this case. So this is how we will solve this question. Now we are going for our next question, question number 10. In question number 10, it is given that electromagnetic radiation of wavelength 242 nanometer is just sufficient to ionize sodium atom. Calculate the ionization energy of sodium in kilojoule per mole. So here we will see that ionization energy per mole, that will be equal to energy of 1 mole of photon, or we can say quanta. So it is given as, this energy of 1 mole of photon is given as nh nu. So n multiplied with h is Planck constant, nu is c upon lambda. Now put the values, that is equal to ionization energy per mole. So here we can see how many number of sodium atoms will be there, that is 6.022 into 10 power 23. H is Planck constant, 6.62 into 10 power minus 2034 joule second, multiply with 3 into 10 power 8 meter per second, divided by lambda. Lambda is 242 nanometer, that is 242 multiplied with 10 power minus 9 meter. Now if I solve this one, it will be 494.6 multiplied with 10 power 3 joule per mole. So I have got the answer in joule per mole. Now I can convert in kilojoule. It will be 494.6 kilojoule per mole. So this is how we will solve this question. Now let's move on to question number 11. Here the question is a 25 watt bulb, means power of the bulb is given as 25 watt, which emit monochromatic yellow light of wavelength 0.57 micrometer. Now they are saying that calculate the rate of emission of quanta per second, that we have to find. We can see here that the power of the bulb is 25 watt. It means that the bulb used to emit 25 joule energy per second. So I have to consider that the energy which is emitted by the bulb will be 25 joules, and it is for 1 second, and the wavelength which is given, it is 0.57 micrometer. So 0.57, when it is multiplied with 10 power minus 6, so it will be getting converted into meter. Velocity of the light is known, that is 3 into 10 power 8 meter per second. So we know that E is equal to nh nu. So n is what? Number of quanta packets, number of quanta, or you can say x will be the quantity of light emitted per second. So here E will be equal to n, h, nu is c upon lambda. So we need to find out n value. So n will be equal to E lambda upon hc. E is given as 25 joule. So we have written here E value as 25 joule. Then lambda value is 0.57 into 10 power minus 6 meter, divided by h value 6.62 into 10 power minus 34 joule second, multiply with c value is 3 into 10 power 8 meter per second. So when it is solved, we will get the value as 7.168 multiplied with 10 power 19. So this many number of quanta packets will be there per second. Let's move to question number 12 now. Here question number 12 is given as the electrons emitted with zero velocity. So we are talking about electrons, and they are emitted with zero velocity from a metal surface when it is exposed to a radiation of wavelength 6800 angstrom. we can convert into meter. 6800 multiplied with 10 power minus 10 meter. Now calculate the threshold frequency, that is threshold frequency we are denoting with nu naught we have to find, and we have to find the work function W naught for the case of the metal. So when the velocity of electron is 0, then the kinetic energy will also be 0, as we know that kinetic energy is given as half mv square. The velocity of the electron is 0, means kinetic energy will also become 0 in this case. We also know that the relationship, that is absorbed energy, is equal to your threshold energy plus the kinetic energy of photoelectrons of photoelectrons. So absorbed energy will be equal to h nu, so E will be h nu equal to threshold energy will be your work function W naught plus the kinetic energy of the photoelectron will be 0. So h nu means h c upon lambda equal to W naught. W naught is the work function. So H value is known, 6.62 into 10 power minus 34 joule second. C value is known, 3 into 10 power 8 meter per second, divided with lambda, that is 6800 multiplied with 10 power minus 10 meter equal to W naught. When I solve this one, I will get the value of W work function as 2.923 into 10 power minus 19 joule. So that will be the work function. Now work function is given as E naught, or in the form of energy, so it will be h nu naught. So this will be threshold frequency. So we need to find out threshold frequency. It will be E naught upon h. The E naught value is same as W naught, that is 2.923 multiplied with 10 power minus 19 joule divided by h, that is Planck constant 6.62 into 10 power minus 34 joule second. When I solve this one, it will be 4.41 multiplied with 10 power, it will be 10 power 14 hertz. So this will be the case, that is the threshold frequency for the case of this metal. Let's have to next question. It is question number 13. In question number 13 is that what is the wavelength of the light emitted when the electron in an hydrogen atom undergoes transition from energy level with n is equal to 4 to n is equal to 2. So this transition is happening. We have to find the wavelength here. So n is equal to 4 will be considered a higher energy level, and when n is 2 is equal to 2, it will be considered as lower energy level. So this will be n2 and this will be n1. Now we can see it is the case of hydrogen atom. So hydrogen atom is having the atomic number Z is equal to 1. Now we will use the Rydberg equation. Rydberg equation. So we have Rydberg equation as 1 upon lambda, that is reciprocal of wavelength, equal to Rz square bracket 1 upon n1 square minus 1 upon n2 square. So 1 upon lambda, lambda means the wavelength we have to find, I think. Yes, wavelength we have to find. As per the question, R value is Rydberg constant, that is 109,677.76 centimeter inverse, that is the Rydberg constant. Then Z value is 1 square bracket 1 upon n1 square, n1 is 2 square minus 1 upon 4 square, higher energy level, lower energy level. Then it will be finally, if I calculate this one, I will get the lambda value as 4.86 multiplied with 10 power minus 5 centimeter. So this is how we will get the wavelength in centimeter. Now if I just convert into meter, it will be 486 multiplied with 10 power minus 9 meter. Then if we can convert into nanometer also, it will be 486 nanometer. Going to question number 14. Here we have question 14 now. How much energy is required? We need to find out how much energy is required to ionize a hydrogen atom if the electron occupy n is equal to 5. That means this fifth orbit it has been occupied. Compare your answers with the ionization enthalpy of hydrogen atom to remove the electron from the first orbit. If first remove electron from first orbit to be done, so how much energy will be required, how much ionization energy will be there? This energy is compared with the energy in the case of fifth orbit. So we can have delta E, that is change in energy. It will be energy in case of infinity minus energy in case of fifth orbit. So energy in case of infinity will be 0 minus, then energy we have to find in case of fifth orbit will be minus z square upon n square into 2.18 multiplied with 10 power minus 18 joule. That is the relationship we have to remember. So it will be 0 minus z square. Z means hydrogen atom, it will be 1 square divided by n means fifth orbit 5 square multiplied with 2.18 into 10 power minus 18 joule. Now solve this one. 0 minus minus plus, it will be considered, so it will be 1 multiplied with 2.18 multiplied with 10 power minus 18 whole divided by 25. When I solve this one, it will be 8.72 multiplied with 10 power minus 20 joule. So this will be the case here. And what is the case for ionization of hydrogen atom when one electron is removed? It is used to be there 2.18 into 10 power minus 18 joule. So the case here we have solved, we have got this much amount of energy, but when the hydrogen atom is losing first electron, then how much ionization energy will be there? It will be this much. So when it is compared, you can see here the comparison value. Now moving to the next question, question number 15. Question 15 is that what is the maximum number of emission lines? We have to find the maximum number of emission lines which when the excited electrons of hydrogen atom in n is equal to 6 drops to ground state, n is equal to 1. So this is the ground state, so this is the higher energy level and this is the lower energy level. So we need to find out what will be the spectral lines. If you want to find the number of spectral lines, in this case we will get the formula, that is n2 minus n1 in bracket n2 minus n1 plus 1 whole divided by 2. So n2 minus n, so it will be 6 minus 1, then 6 minus 1 plus 1 whole divided by 2. 6 minus 1 5, multiply with 6 minus minus cancel, it will be 6 divided by 2. 6 5 30, 30 upon 2, that is 15. So it will be 15 number of spectral lines will be present here. Let's have to the next question, that is question number 16. In question number 16 we have some parts. In the first part, the question is given that the energy associated with the first orbit of hydrogen atom we are talking about first orbit presence, and the energy which is associated is given as 2 point minus 2.18 multiplied with 10 power minus 18 joule. Then they are asking that what is the energy associated with fifth orbit. This is for first orbit. So for the same case of hydrogen atom, so we have to find out. So we know that energy for the nth orbit will be given as minus E1 divided by n square, so divided by n square. Now it will be E1, so minus E1 means it is minus 2.18 multiply with 10 power minus 18 divided by n square means 5 square that is 25. So minus 2.18 multiply with 10 power minus 18 divided by 25. When I solve this one, it will be minus 8.72 into 10 power minus 20 joule. So this much amount of energy will be associated when it is the case of fifth orbit. Now we have second part also. Here second part is that uh, what is the okay, calculate the radius of the Bohr orbit, fifth orbit of hydrogen atom. So we have to calculate the radius for the case of radius that is fifth orbit of the hydrogen atom. So we have the formula that radius will be equal to n square upon z multiplied with 0.529 angstrom. So here it will be n square means it is 5 square, 5 5 is 25 divided by z. Z value is 1, that is for hydrogen atom, multiply with 0.529 angstrom. Now solve this one. 5 5 25 multiply with 0.529 angstrom. Now we can convert into meter. It will be 1 point, I can convert, first of all I will multiply, it will be 13.225 angstrom. We can convert into meter, it will be 1.3225 nanometer. So we have converted the value in nanometer also. So this is how we are solving this question. Let's have next question. Question number 17. In question number 17 we can see we have to calculate the wave number nu bar for the longest wavelength transition in the Balmer series. So we are talking about Balmer series, and the transition is happening for the case of atomic hydrogen. So here we can see that we will be using the Rydberg Rydberg equation. So it will be 1 upon lambda, that is equal to r z square in bracket 1 upon n1 square minus 1 upon n2 square. So 1 upon lambda is wave number, so nu bar will be there. R value is given 0.109676 centimeter inverse, that is the Rydberg constant. Multiply with z square, that is hydrogen, that is will be 1 square in bracket 1 upon n1 square. So n1 will be for Balmer series. Balmer series will be having n1, that is 2, and n2 will be 3. So it is n1 square, that is 2 square minus 1 upon 3 square. In bracket it will be considered in this way. So 109676 centimeter inverse multiply with 1 upon 2 square 4 minus 1 upon 3 square 9. Now it will be 109676 centimeter inverse multiply with taking the LCM, 9 4 36. So 9 4 36, 4 4 16. It will be 16 minus 9 4 4. So it will be 8 upon 36. When I solve this one, it will be somewhat 1.523 multiply with 10 power 6 meter inverse. So in this way we will solve this question. Let's have question number 18 now. In question number 18 it is given that what is the energy in joule required to shift an electron of hydrogen atom from first Bohr orbit to fifth Bohr orbit. What is the wavelength of light emitted when the electron returns to the ground state? When it is returning back to the ground state, the ground state electron energy, the ground state electron energy is given as minus 2.18 into 10 power minus 11 ergs. Let us solve this one. We have change in energy, that is delta E, that is will be equal to E2 minus, that is E5 minus E1. So E5 minus E1 means it will be energy equation is known that it will be energy equation is known, that is E base n equal to minus E1 divided by n square. So it will be the energy in the first orbit is given, that is in the ground state it is given. So it will be minus 2.18 multiplied with 10 power minus 11 divided by 5 square, it is 5 minus it will be minus 2.18 multiplied with 10 power minus 11 whole divided by 1 square, that is 1. Now solve this one. If we solve this one, it will be getting out to 24 upon 25, 24 upon 25 multiply with 2.18 multiply with 10 power minus 11 arcs. So in this way we have come across the solution. Let's move on to the next case, but before that we can finalize the answer in joules also. 2.0928 multiply with 10 power minus 18 joule. So this will be the final answer for this case. Now in this question we have to find out the wavelength also. We know that delta E is equal to h nu. H nu means c upon lambda. So here we need to find out the lambda. So lambda will be equal to hc upon delta E. So h is given 6.62 into 10 power minus 34 joule second. C's value is given as 3 into 10 power 10 power 8 meter per second divided by delta E value is 2.0928 multiply with 10 power minus 18 gram, 10 power minus 18. So when we solve this one, it will be get as 949.8 angstrom. So we will get this value, and in this way we will solve this question. Now we will solve question number 19. Here in question number 19 it is given that the electron energy in hydrogen atom is given by E base n equal to minus 2.18 multiplied with 10 power minus 18 upon n square joule. This is the electron energy in case of hydrogen atom. Now we have to find that calculate the energy required to remove the electron completely from n equal to 2 orbit. We have to remove the electron from second orbit. What is the longest wavelength of light in centimeter that can be used to cause this transition? So here we know that E base n equal to minus 2.18 multiplied with 10 power minus 18 divided by n square. So therefore energy will be there for second orbit, it will be minus 2.18 multiplied with 10 power minus 18, it will be 2 square joule. So solve this one, it will be minus 5.45 multiplied with 10 power minus 19 joule. Now the energy required to remove the transition to remove the electron from the n second orbit, that will be delta E equal to E infinity minus E2. So E infinity will be 0 minus energy from the second orbit will be minus 5.45 multiplied with 10 power minus 19 joule. It will be 5.45 multiplied with 10 power minus 19 joule. Now we need to find out the wavelength of light which is required to cause above transition, this transition which is happening. So the wavelength will be, in this case we know that delta E is equal to h nu. H nu means h multiplied with c upon lambda. Now lambda will be equal to hc upon delta E. So h is Planck constant 6.62 multiplied with 10 power minus 34 joule second. Then c is 3 multiplied with 10 power 8 meter per second whole divided by delta E. Delta E is 5.45 multiplied with 10 power minus 19 joule. Now if I solve this one, it will be 3647 multiplied with 10 power minus 10 meter, and we have to find the answer in centimeter. So we can have 3647 multiplied with 10 power minus 8 centimeter. So this is the final answer. Moving to question number 20. In question number 20, it is calculate the wavelength of the electron moving from with a velocity of 2.05 multiplied with 10 power 7 meter per second. So we know that the de Broglie equation, that is lambda is equal to h upon mv. So we can find here h is Planck constant 6.62 into 10 power minus 34 joule second divided by mass of electron is known 9.10 multiplied with 10 power minus 31 kg. Then velocity is given, velocity of electron which is moving, it is given as 2.05 multiplied with 10 power 7 meter per second. When we calculate this equation, we will get it down as 3.55 multiplied with 10 power minus 11 meter. So this is how we will find the wavelength here by using de Broglie equation. Let's go out for our question number 21. In question number 21, it is given the mass of electron is given. Mass of electron is given as 9.10 multiplied with 10 power minus 31 kg. And if its kinetic energy is itna, so kinetic energy is also given here, that is 3.0 multiplied with 10 power minus 25 joule. This is the kinetic energy. We have to find the wavelength. So we have the de Broglie equation, see, that is lambda equal to h upon mv, and we can have adjusted this particular equation in this form. If the kinetic energy of the particle is given, then we will be using this de Broglie wavelength in this way. Lambda is equal to h upon root over 2 em, that is the mass. So it will be lambda is, we have to find h value is 6.62 multiplied with 10 power minus 34 joule second divided by root over 2 multiplied with e value is energy, and that is the kinetic energy which is known, that is 3 multiplied with 10 power minus 25 joule. Then mass of electron is 9.10 multiplied with 10 power minus 31 kg. Now if we solve this one, we will be getting as 8.967 multiplied with 10 power minus 7 meter. Now just converting to nanometer, it will be 896.7 nanometer. So this will be the answer for this solution, for this question. Now we have reached to question number 22. Let's move to question number 22 here. We can see here which of the following are isoelectronic species. So they are talking about isoelectronic species. It means these species will be having same number of electrons. Now a pair of species have been given and we have to find out how many number of electrons are there. So in case of sodium, we will see atomic number is 11. So if atomic number is 11 and it is n positive, so it will be 11 minus 1, that is 10 electrons are there. In potassium, atomic number is 920. Then atomic number of potassium is chlorine, then argon, and calcium 19. So 19, atomic number is 19. When I remove plus K positive, so it will be removing 1 electron, it will be 18 electrons. Now for magnesium, atomic number is 12, removing 2 electrons, it will be 10 electrons. And for calcium, atomic number 20, removing 2 electrons, it will be 18 electrons. For sulfur, it is atomic number 16, adding 2 electrons because it is sulfide ion, so it will be 18 electrons. And for argon, it is 18, atomic number 18, and it is 18 electrons. So we have categorized these isoelectronic species as First category having 10 electrons, so it will be case of sodium ion, and it is a case of magnesium ion. Second category is having the presence of 18 electrons, that is potassium ion. Then we have calcium ion, then we have sulfide ion, and then we have argon. Move to next question, that is question number 23. Write down the electronic configuration for the following ions. The first one is hydride ion. So hydrogen is having atomic number 1. So if it is atomic number 1, it will be having 1 electron. Now as it is hydride ion, so 1 electron is added, so it will be 2 electrons. So it will be 2 electron, means the configuration will be 1s2. Second one we have sodium ion. Sodium ion atomic number is 11, so 11 electron is there, and as it is Na positive, so we have to remove 1 electron. Remove 1 electron, it will be 10 electrons, so it will be 1s2, 2s2, 2p6, then 3s0. For sodium, if it is sodium atom, then it will be 3s1. As we have removed 1 electron, so 1 electron is absent here. Next one we have third one, that is O2 negative. So oxygen atom is there. Oxygen atom is having atomic number 8, having 8 electrons. So if it is 8 electrons, it will be 1s2, 2s2, 2p4. Now it is oxide, we have to add 2 electrons more, so then it will be 10 electrons, so it will be 1s2, 2s2, 2p6. D1 we have here, that is fluoride ion. Fluoride means fluorine atom, 9 electrons, 9 atomic number, so it will be 1s2, 2s2, 2p5. And if it is a fluoride ion, then we have to add 1 electron more, so it will be 10 electrons, so it will be 1s2, 2s2, 2p6. So this is how we have come across these electronic configurations. Now this is the first part of the question. In the second part, they are saying that what are the atomic number of the element whose outermost electrons. So here they have given outermost electrons are represented by this. Here A is given as 3s1. We have to tell the atomic number of that element. So 3s1 means before 3s1, what are the orbitals which are present, which are completely, it will be 1s2, then it will be 2s2, then 2p6, then it comes to 3s1. So 6 plus 2 8, 8 plus 2 10, 10 plus 1 11, so it will be 11 atomic number element, so it is sodium. Now we have B, it is 2p3, so before 2p3 it is 1s2, 2s2, then 2p3, 3 plus 2 5, 5 plus 2 7, so atomic number 7, 7 electrons are there. So 7 electron means 7 atomic number. 7 atomic number used to be there for atomic number 7 is for nitrogen. Then we have C case, that is the 3p5. It is 3p5 means 1s2, then 2s2, then it will be 2p6, then 3s2, and then 3s2, it is 3p, it is 3p, it is not 3p5, it is 3d6, 3d6. So if it is 3d6, the case of 3d6, so it will be 1s2, 2s2, 2p6, then 3s2, then 3p6, then we have 3d, 3p6, then 3d6, and we have 4s2 also. 4s2 we are writing here, but it actually comes to be there before 3d. So that is, if it is the case of 3d6, it will be having 2 plus 2 4, 4 plus 6 10, 12, 18, 20, 26. So it is having 26 electrons. means atomic number 26, it is for iron. If this question is of case of 3p5, then it will be 1s2 2s2 2p6 3s2 3p5. So it will be 5 plus 2 7, 7 plus 6 13, 14 15 16 17. 17 electrons will be there having atomic number 17, and it will be chlorine. Moving to the third part of the question, and in the third part it is given that which atoms are indicated by the following configuration. So first one is given as helium, then it is 2s1. So helium 2s1, hydrogen helium 2, then 3, it is 3. So 2 plus 1 3, that is atomic number is 3, that is lithium. Then we have second one, that is neon. Neon, it will be 3s2 3p3. So neon is 10, and 2 plus 3 5, so 10 plus 5 15. So 15 atomic number is for phosphorus. Then we have third one, organ, then 4s2 and 3d1. So organ is 18 and node 21. 21 atomic number is there, it is for scandium. So this is how we have come across up to these questions. Let's move to the next question. पूजा आवाज कम कर दे. Now we have question number 24. Question is, what is the lowest value of n that allows g orbital to exist? S, P, D, F. When S, for S orbital, L value, that is azimuthal quantum number, is 0. For P orbital it is 1. For D it is 2. For F it is 3. Then for G orbital it is 4. So L value is 4 for the G orbital. So if you want to find out the lowest value of n, therefore n is given as L plus 1. So it will be 4 plus 1, that is 5. So for n equal to 5, the G orbital will exist. Go for the next question now. Question number 25. An electron is in one of the 3D orbital. We have 3D orbital. So it will be 5D orbitals are there. 1, 2, 3, 4 and 5. D, X, Y, D, Y, Z, D, ZX, D, X square, Y square and D, Z square. So an electron is there in any one of the 3D orbital. Give the possible values of n, that is principal quantum number, L, azimuthal quantum number, and m base L, that is magnetic quantum number. So we can see here it is 3D orbital, means n value is 3. The coefficient here is indicating the principal quantum number. Then we can see here s orbital, p orbital, d orbital and f orbital. When s orbital is there, L value is 0. When p orbital is there, L value is 1. When d orbital is there, L value is 2. So it is 3D orbital, means here the L value is 2. Now when L value is 2, then the possible magnetic quantum number will be -2, -1, 0, 1 and 2. So in this way we will solve this question. Moving to question number 26. An atom of an element contains 29 electrons and 35 neutrons. Deduce the number of protons and the electronic configuration of the element. So we know that your mass number means number of protons plus number of neutrons, and your atomic number is means number of protons, that is equal to number of electrons if the atom is neutral. So if the atom is neutral means number of protons is not given, number of electron is given. Number of electron is 29. It means here the number of protons will be 29 and the atomic number will also be 29. So we have got that number of protons will be 29 protons. Now what about the electronic configuration? If there are 29 protons, it means the atomic number is 29. So the element which is having atomic number 29 is copper, and this copper is having some specific configuration. Let us write up this configuration. It is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. But here we see a change in the configuration. It is 1s2, 2s2, 2p6, 3s2, 3p6, then it will be 3d10 and 4s1. So this configuration is considered for copper. Moving to question number 27, it is give the number of electrons which are present in this species. One is H2 positive, another one is H2, another one is O2 positive. So we have to find the number of electrons. We can see here hydrogen. When I say hydrogen atom or hydrogen element, it is having one electron. Atomic number of hydrogen is 1 and it is having the presence of one electron. So 2 hydrogen means 2 electrons will be there, 1 plus 1 electron, and it is having one positive charge, so it will be -1. So finally we will get the presence of 1 electron. For H2 it will be having 1 plus 1 electron, that is 2 electrons. For oxygen, O2 positive, we can see here oxygen atom is having atomic number 8, so it will be having the presence of 8 protons and 8 electrons. So 8 electrons plus 8 electrons and having a positive charge -1, 16 minus 1, that is 15 electrons. So it will be having 15 electrons here. Moving to question number 28 now. An atomic orbital has, the first part we can see, atomic orbital has n value as 3. What are the possible values of L and M base cell? That is, we have to find the azimuthal quantum number and your magnetic quantum number. We can see here this is our principal quantum number which is given. So when n value is 3, L value used to be from 0 to n minus 1. So it will be 0 to 3 minus 1, 0 to 2, that is 0, 1 and 2. Now M base L value depend on L. It will be when L value is 0, then M base L value will be 0. When L value is 1, then magnetic quantum number will be -1, 0, plus 1. When L value is 2, magnetic quantum number will be -2, -1, 0, 1 and 2. So in this way we will find the possible values of L and M base L. We have the second part here. In the second part we can see list the quantum numbers, magnetic quantum number and azimuthal quantum number of electrons for 3D orbital. So we have 3D orbital where electrons are present. So when I say 3D orbital, it means n value is 3, that is the principal quantum number. If it is d orbital, this indicate that your L value will be 2, that is for d subshell. Now when L value is 2, then magnetic quantum number will be -2, -1, 0, 1 and 2. So these values will be present. In the third part of the question, we can see here the question is which of the following orbitals are possible. Here 1p, 2s, 2p and 3f. These orbitals have been given. So out of these, which orbitals are possible? We can see here 2s orbital is possible and your 2p orbital is possible. So 2s and 2p orbitals are possible. This 1p orbital is not possible, and 3f orbital is also not possible. We can check once. When I say 1p orbital, what does it mean? It means that n value is 1, and the p orbital is indicating that we know that s, p, d, f means L value is 0, 1. So if p orbital is there, so L value will be 1. Then whether it is possible, we can see here it is not possible category. Similarly for 3f orbital also it is not possible. Let's move on to our next question, that is question number 29. Using SPDF notations, you describe the orbitals with the following quantum numbers. So first case we have n value is 1 and L value is 0. What does it mean? So if n value is 1 and L value is 0, so we know that S is indicating 0 L value, then P, then D and F. 1, 2, 3. These are the L values, that is your azimuthal quantum number. N value is 1 means 1, L value is 0 means S. So it is your 1s orbital. Second one we have n value is equal to 3 and L value is equal to 1. So we can see here L value is 1 means it is 3p orbital. Third part we have n value is 4 and L value is 2. It means it is 4d orbital. And fourth part we have n value 4 and L value 3. It is 4f orbital. So in this way we have to describe the orbitals. Moving to question number 30. Explain, giving the reason, which of the following sets of quantum numbers are not possible. So which of the following sets are not possible? So we can see here one by one. If we take the first one where we find n value as 0, so this is not possible because if n value is 0, this is not indicating any orbital. It is indicating basically a principal quantum number. As we can see, if n value is 0, so L value they are indicating, because possible values of n are 1, 2, 3. N value used to be 1, either 2, either 3, but it is not like that here. So this case is not possible. Second, we can have C value, C part, that is also not possible. When n value is 1 and we can see here n value is 1 given and L value is also 1 given, and but we know that when n value is 1, L value used to be there from 0 to n minus 1. So 0 to 1 minus 1, 0 to 0, that is 0. But here they have given L value as 1, so this case is also not possible. Then we have another case, that is E case. We can see n value is 3 given, L value is 3 given. Whether this case is possible, Here also we can see when n value is 3, so n value is to be there from 0 to n minus 1, that is 0 to 3 minus 1, that is 0 to 2, 0 1 and 2. But here n value they have given as 3, so this case is not possible. So these three cases are not possible here in this question, whereas other cases are possibly correct. Now we are with our next question, that is question number 31. In question number 31, it is given that how many electrons in an atom may have the following quantum numbers. So the case is first A, when n value is 4 and spin quantum number is given as minus half. So we have to find the total number of electrons here in a shell. So n value is 4 means how many electrons we can find, it will be given as by 2n square. So 2 multiplied with 4 square, that is 4 4 16, 16 2 32. So it will be 32 electrons. Now as the spin quantum number is given only the one part, so it will be half, because another spin quantum number is m base s is equal to plus half. So for minus half they are asking, it will be considered as 16 electrons, that is having anti-clockwise spin, anti-clockwise spin. In the B part, here the n value is 3 and L value is given as 0. We can see here that n value is 3 means 3 and L value is 0 means s, so 3s orbital. This indicates 3s orbital. So it will be having how many electrons maximum? So it will be having maximum of 2 electrons, because s orbital can occupy a maximum of 2 electrons. So maximum of 2 electrons are present here in this case. Moving to question number 32. Here the question is, show that the circumference of Bohr orbit for the hydrogen atom is an integral multiple of the de Broglie wavelength associated with electron revolving around the orbit. So it can be shown by this equation, where we can see the angular momentum of the electron can be calculated as, that is mvr equal to nh upon 2 pi. So we just have to arrange 2 pi will be shifted here, 2 pi r equal to nh upon mv, then 2 pi r indicate the circumference of the orbit, and it will be 2 pi r equal to n h upon mv is indicating de Broglie wavelength, so it will be n lambda. So we know that lambda is equal to de Broglie wavelength is given as nh upon, that is h upon mv, h upon mv, and your this particular part, it means here the angular momentum of electron, angular momentum of electron is calculated by this. So we have shown that how the circumference of the Bohr orbit of hydrogen atom is an integral multiple of de Broglie wavelength, 2 pi r equal to n lambda. Moving to question number 23. In question number 33, it is given as, what is the transition in the hydrogen spectrum would have the same wavelength as the Balmer series or Balmer transition when n is equal to 4 to n is equal to 2 of helium ion, helium LeHe positive spectrum. So we have to find here, it will be 1 upon lambda. We have to find use the Rydberg formula, Rydberg equation, 1 upon lambda equal to r z square equal to, that is bracket, 1 upon n1 square minus 1 upon n2 square. Put the values there. 1 upon lambda, that is 1 upon lambda, lambda of what, helium He positive ion, equal to r multiple z, z is what, atomic number of helium, that is 2 square, 2 to square is 4, bracket 1 upon n1 square is 2 square minus 1 upon 4 square. So 1 upon lambda He base positive equal to 4r, then here it will be 1 to the 4 minus 1 upon 4 4 16. So after solving this one, we will get as 1 upon lambda that is for He positive equal to 3R upon 4. So this equation we have got for helium ion. Now what about for hydrogen? 1 upon lambda base hydrogen equal to R Z square bracket 1 upon N1 square minus 1 upon N2 square. So it will be 1 upon lambda base H equal to R Z square means 1 square 1 upon N1 square minus 1 upon N2 square. Now this having the same wavelength for hydrogen also and for He positive also, so they have the same wavelength, means we can equate this one. So it will be 3R upon 4, that is equal to R and bracket 1 upon N1 square minus 1 upon N2 square. R and R get cancelled, so it will be now 3 upon 4 equal to 3 upon 4 equal to 1 upon N1 square and 1 minus 1 upon N2 square. So here it will be N1 is equal to 1 and N2 is equal to 2. If these values will be taken, so we can see here the transition will be from n equal to 2 to n equal to 1. So in this way we will solve this question. Moving to question number 34, calculate the energy required for the process, that is He positive gas state gives you He2 positive plus electron, means here loss of electron is happening. So how much energy is required? The ionization energy for hydrogen atom, ionization energy for hydrogen atom in the ground state is given as 2.18 into 10 power minus 18 joule per atom. So we can use this equation that ionization energy for hydrogen atom, ionization energy for helium ion is equal to atomic number whole square for hydrogen, atomic number for helium whole square. So it will be 2.18 multiplied with 10 power minus 18 divided by ionization energy of helium ion He positive equal to 1 square upon 2 square. So it will be cross multiplying, so we will get ionization energy for helium ion, it will be 8.72 multiplied with 10 power minus 18 joule per atom. So this way we will solve this question. Now we are with question number 35. Question number 35 is given as, if the diameter of the carbon atom, so we are talking about carbon atom, and the diameter of the carbon atom is given as 0.15 nanometer. Calculate the number of carbon atoms. We need to find out the number of carbon atoms which can be placed side by side in a straight line across the length of scale. Length of the scale is 20 centimeter long. So we can see here, let how many x atoms of carbon can be placed in a length of the scale 20 centimeter. X atoms could be placed here. So X atom is there. So a single atom, each atom is having a diameter of how much? That is 0.15 nanometer. This much diameter is there for different atoms. So it will be 20. Now x multiplied with 0.15 into 10 power minus 7. It will be now in meter. So equal to 20. Then x will be equal to 20 upon 0.15 into 10 power minus 7. When I solve this one, it will be 1.33 into 10 power 9 atoms. So in this way we can get here that how many number of atoms will be adjusted in a length of the scale, that is 20 centimeter, when we are placing these atoms, the carbon atoms, that is having diameter of 0.15 nanometer. Now let's have question number 36. In question 36 it is given that 2 multiplied with 10 power 8 atoms. So these many number of atoms are there that are arranged side by side, like in this way, side by side. These many number of atoms are arranged side by side. Now we have to find this. It is given as number of atoms. Now calculate the radius of the carbon. We have to find the radius of carbon atom, radius for carbon atom. If the length of the arrangement, here the length of arrangement is given as 3 centimeter. So we know that there are x number of atoms are there. This x number of atoms will be having a diameter d, then it will giving a length. That length is 3 centimeter. So we can find here the length is given as 3 centimeter. So x means the how many number of atoms are there, that is 2 into 10 power 8 number of atoms are there. Each will be having some diameter. The diameter is given. So we can get this value as diameter equal to 3. So d will be 3 upon 2 into 10 power 8. So we will get as 1.5 into 10 power minus 8 centimeter. Now it is in centimeter, we can just divide by 2. We can get the radius 1.5 into 10 power minus 8 divided by 2. It will be 0.75 into 10 power minus 8 centimeter. So this will be in terms of centimeter. Now we can convert into meter. So it will be 0.075 into 10 power minus 9 meter, and we can also calculate in terms of nanometer, 0.075 nanometer. So that will be the radius of the carbon atom. Moving to question number 37. In question number 37 it is given that the diameter of zinc atom. So let us see, here we have a zinc atom. This is the diameter d. It is given as 2.6 angstrom. We have to calculate the radius of zinc atom in picometer. Second, we have to calculate number of atoms. Number of atoms we have to calculate, that is present in the length of 1.6 centimeter. Like in this way, it is arranged side by side. So let us solve this one. If the first part is there, so we know that half of the diameter is the radius. If diameter is given 2.6 angstrom, it means 2.6 divided by 2, it will be 1.3 angstrom. That is the radius of the atom. This can be converted into meter, that is 1.3 is multiplied with 10 power minus 10, then it will be in meters. And if we want to calculate in picometer, so we can just this is a meter value. Now we can calculate in picometer also. So it will be now 130 multiplied with 10 power minus 12 meter. I have just shifted the value, I have shifted the point. So it will be 130 multiplied with 10 power minus 12. So now it will be 130 picometer, because in 1 picometer it is 10 power minus 12 meter. So it will be 130 picometer. Now what about the second part? Here we need to find out there are x number of atoms, let it be. Each atom is having some diameter d. Then each atom is arranged side by side, and it is giving a length of 1.6 centimeter. So x number of atoms, that is diameter, is how much? 2.6 angstrom, means 2.6 into 10 power minus 8 centimeter equal to 1.6. Now it will be x value will be 6.154 into 10 power 7 atoms. So this many number of atoms are there side by side. For the case of zinc atom, that zinc atom is having a diameter of 2.6 angstrom. Now we are with our next question, that is question number 38. We can have a certain particle that carries 2.5 multiplied with 10 power minus 16 coulomb of charge. So this is a charge which the substance or the particle is carrying. We have to find the number of electrons, present there. So it is given as n number of electrons are there. Each electron will be having some charge, that is q by c. How many electrons are there? N number of electrons are there. Each electron will be having some charge. Now here they are saying that particle carries this much charge. So how much charge is there? That is 2.5 into 10 power minus 16. This particle will be having n number of electrons. Each electron will be having some specific charge. So this is n number of electrons. The electron charge is, single electron charge is 1.6 into 10 power minus 19 coulomb, equal to 2.5 into 10 power minus 16. So it will be solved now. N value equal to 2.5 into 10 power minus 16 divided by 1.6 into 10 power minus 19. After solving, we will get as 1562 electrons. So these many electrons will be present there. Let's move to question number 39. It is, in a Millikan experiment, static charge on the oil drop has been obtained by shining X-ray. If the static electric charge on the oil drop is this much, so what charge is there? The static charge which is given on the oil drop is minus 1.282 into 10 power minus 18 coulomb. This much charge is there. We have to calculate the number of electrons. How many electrons are there? So total charge is minus 1.282 into 10 power minus 18 coulomb. So there are n number of electrons. Each electron is having some charge. So we can get this n value now. We can get this n value. Here there is a question mark. So n value is equal to 1.282 into 10 power minus 18 coulomb divided by the charge of electron, that is 1.6 into 10 power minus 19 coulombs. When we solve this one, it will be given as 8 electrons. So there are a presence of 8 electrons here. Now we are with question number 40. In this question, it is given that Rutherford experiment is performed. Generally, the thin foil of heavy atoms like gold, platinum have been used to be bombarded by the alpha particles. The thin foil of light atoms like aluminium is used. What difference would be absorbed from the above result? So they are taking a comparison in this question, and we have to indicate that what will be possible result if you are using thin foil of aluminium. So we can see here that the heavy metals have high positive charge. Heavy metals is having high positive charge, and hence they are capable enough of deflecting, able to deflect positively charged alpha particles. And in case of your lighter items like aluminium, the deflection of alpha particles will be insignificant or will not be proper. Deflection of alpha particles will be insignificant, or we can say it is not proper. Moving to question number 41. Here symbols of bromine is given. Bromine 3579 and bromine 79, that is the mass number is given. Now can be written, whereas symbols of bromine 7935 and bromine 35 are not acceptable. So this is acceptable, but this one is not acceptable. We have to answer briefly. We can see here, while writing the symbolic representation, mass number is written here, atomic number is written here, and mass number is written here. Mass number is written as a superscript and atomic number is written as a subscript. So that is why this one is acceptable. Moving to question 42. Here question is an element with mass number as 81 containing 31.7% of more neutrons as compared to protons. Assign the atomic symbol. We have to indicate atomic symbol for this question, for this particular element. So we have to consider how many number of protons are there. Let we are considering that in an element the number of protons are x. Number of protons we have considered for that element is x. Now as per the question they have given that 31.7%, it will be 131.7 divided by 100 of protons x. It is 31.7% more neutrons than protons. So if you considering it will be number of neutrons. So we have got this here. Number of neutrons will be 131.7 divided by 100 multiplied with x. Now it will be 1.317x. Now the mass number is given as number of neutrons plus number of protons. So mass number is given as 81. Number of neutrons we have got 1.317x plus number of proton is x. So x plus 1.317x, it will be 2.317x equal to 81. Then x will be equal to 81 divided by 2.317. So it will be 34.95, that is approximately 35. So we can have that bromine is having atomic number 35 with mass number 81. Moving to question number 43. In this question we are talking about ion with a mass number 37 and it possesses 1 unit negative charge. Means let us here this particular atom is there in ionic form having charge -1. If the ion contain 11.1% more neutrons than electrons, find the symbol of the ion. We have to find the symbol of ion. So let the number of electrons present in the ion be x. So the x I have considering as number of electrons in that element. So what they are saying that number of neutrons will be equal to 11.1% more than more neutrons than electrons. So electrons number is x plus 11.1 upon 100 of x. So it will be 1.111 x. These many number of neutrons are there. Now we can see here mass number is equal to number of neutrons plus number of protons. Now we can see as number of electrons in a neutral atom. How many electrons will be there if it is a neutral atom? So number of electrons will be, as there are x electron minus 1, so it will be x minus 1 number of electrons will be there in the neutral atom. So we can take number of neutron as 1.11x plus the number of protons and number of electrons will be equal if the atom is neutral. So if the atom is neutral, then the number of electron is given as x minus 1. So x minus 1. Now add this one, we will get the value as we can have the mass number as 37. So finally we will get x value as 18. X value is 18. Then x is number of electrons in this particular ion. Now we need to find out the number of electron in the neutral atom. So it will be 18 minus 1, that is 17. It means that the 17 atomic number is for chlorine, having mass number 35, and it is having a charge minus 1. So this will be the correct symbolic representation for the ion which is present in this case. Now we are with the next question, that is question number 44. Here it is given that an ion with mass number 56 containing 3 unit positive charge, 3 unit positive charge is there, and 30.4% more neutrons are there than comparison to electrons. We have to give the symbol of ion. So how many electrons are there? Let it be x electrons are there in the ion. Then how many protons will be there? The number of protons will be how many? Number of protons will be x number of electrons will be there, then plus 3. This many protons will be there. Now as for the question, it is number of neutrons will be 130.4 x divided by 100, that is 1.304 x. These many neutrons are there. Now mass number is equal to number of protons plus number of neutrons. So mass number is 56, number of protons is x plus 3, number of neutrons is 1.304 x. Solve this one, x value will be 23. So x value is 23, means this many electrons are there in the ion. So for neutral atom it will be x plus 3, that is 23 plus 3, that is 26. So it is iron 26, 56 having charge 3 positive. So this will be the symbolic representation for the ion which is present in this case. Going for question number 45. In question number 45 is we have to arrange the following types of radiation in increasing order of frequency. Here they have given radiation of microwaves, that is microwaves radiations from microwave oven, that is microwaves, amber light of traffic signal, radiation from FM radio, cosmic rays from outer surface, space, and X-rays. So we have to arrange in increasing order of the frequency. So least will be having FM waves, then more it is microwave, then we have traffic light, then we have X-rays, and then we have cosmic rays. These rays will be having maximum frequency. FM waves from FM radio, or the radiations from FM radio, having least frequency. Going for question number 46. In 46 it is talking about nitrogen laser produces a radiation at a wavelength of 37.1 nanometer. If the number of photons emitted is 5.6 into 10 power 24, these many photons are emitted here, these many number of photons are emitted, and calculate the power of laser. We have to calculate the power of laser. So we can have the relationship E equal to NH nu. N represent number of photons, H Planck constant, nu is C upon lambda. Just put the values, how many number of photons are there? 5.6 into 10 power 24 multiply with 6.62 into 10 power minus 34 joule second. C is speed of light, 3 into 10 power 8 meter per second, whole divided by wavelength is 337.1 into 10 power minus 9 meter. After solving this one, we will get a value that is 3.289 multiplied with 10 power 6 joule. So this will be the energy, that is the power of the laser. Come to question number 47. In question 47, it is neon gas is generally used in the signboards. If it emits strongly at wavelength of 616 nanometer, we have to calculate the frequency of emission. Then we have to calculate the distance traveled by the radiation. And C, we have to calculate the energy of the quantum. D, we have to calculate the number of quanta present if it produces 2 joule of energy. So we have frequency is equal to C upon lambda. C value is 3 into 10 power 8 meter per second divided by lambda, that is 616 into 10 power minus 9 meter. Solve this one, we will get as 4.87 into 10 power 14 hertz. So this will be the frequency in this case. Second, we have to find the distance. We know that distance is equal to speed into time. So here speed is 3 into 10 power 8 meter per second, and time they have given as 30 seconds. So it will be 9 into 10 power 9 meter. Third case, we have to find energy. Energy is equal to h nu. H is 6.62 into 10 power minus 34 joule second, multiply with nu, that is frequency, 4.87 into 10 power 14 hertz. Multiply this one, we will get this value as 3.227 into 10 power minus 19 joule. So we have got this value. Now comes to the D part, that is quanta number of packets we have to find. So let it be n number of quantas are there when energy 2 joule is produced. So energy is equal to x n number of quantas and energy of one quanta. So energy of one quanta. So this energy they have given as 2 equal to n number of quanta packets. Energy of one quanta is 3.227 into 10 power minus 19 joule. Then n value we can get as 6.2 into 10 power 18. So these many number of quanta packets are there when 2 joule of energy is produced. Moving to now, let's solve question number 48. So here in this question we can see that in an astronomical observation, signals observed from the distant stars are generally weak. If the photon detector receives total of 3.15 multiplied with 10 power minus 18 joule of radiation of 600 nanometer wavelength. So this is a wavelength and this is the energy. Calculate the number of photons. We have to calculate the number of photons received by the detector. So we know that E is equal to NH nu. N indicate the number of photons. So here we can see NH nu. Nu is C upon lambda. So we have E value as it is 3.15 multiplied with 10 power minus 18 joule equal to N. We need to find out H value is 6.62 multiplied with 10 power minus 34 joule second, multiply with C, that is 3 into 10 power 8 meter per second, divided by lambda. Lambda is 600 nanometer means 600 multiplied with 10 power minus 9 meter. Now if we calculate, we will get this n value as 9.545 multiplied with 10 power 0. So it will be 9.4545, that is approximately equal to 10. So this will be 10 photons which will be present here. Moving to question number 49. In this question we can see lifetimes of a molecule in the excited state are often measured by using pulse radiation source of duration during nearly a nanosecond range. If the radiation source has the duration of 2 nanosecond and the number of photons emitted during the pulse source is 2.5 multiplied with 10 power 15, that is indicating the n value, that is number of photons. Now we have to calculate the energy of the source. So time period is given capital T, that is 2 nanosecond. So this 2 nanosecond could be converted into second, that is 2 multiplied with 10 power minus 9 second. Now we knew that frequency is 1 upon T. So 1 upon T means 1 upon 2.5 2 multiplied with 10 power minus 9. So it will be 5 multiplied with 10 power 8 second inverse. So that will be the frequency. We know that E is equal to NH nu. As we need to find out the energy, so it will N value is given as 2.5 multiplied with 10 power 15. H is known, 6.62 into 10 power minus 34 joule second, multiply with nu, that is frequency, 5 multiplied with 10 power 8 second inverse. After calculating, we will get the value as 8.25 multiplied with 10 power minus 10 joule. So this much amount of energy will be there for the source. Now let's have question number 50. So in this question it is given the longest wavelength doublet absorption transition is observed at 589 nanometer and at 589.6 nanometer. Calculate the frequency of each transition and energy difference, that is delta E between two excited state. So here lambda 1 is given as 589 pico nanometer, so it will be 589 multiplied with 10 power minus 9 meter. Now it is lambda 2, that is 589.6 nanometer, so it is 589.6 multiplied with 10 power minus 9 meter. Now we know that nu is equal to C upon lambda, so lambda will be equal to C upon nu. So we can just see here nu 1 we need to find out, it will be C upon lambda 1. So 3 multiplied with 10 power 8 meter per second divided by lambda 1, that is 589 multiplied with 10 power minus 9 meter. When we solve this one, we will get the value as 5.093 multiplied with 10 power 14 second inverse. The second part, here we can see nu 2 will be equal to C upon lambda 2. C value is 3 into 10 power 8 meter per second. Now divided by lambda 2, it is 589.6 multiplied with 10 power minus 9 meter. Now if we solve this one, it will be 5.088 multiplied with 10 power 14 second inverse. So this is what nu 2 is there. Now we can have the finding for delta E. Delta E will be equal to E1 minus E2. So it will be H nu 1 minus H nu 2. So H common, nu 1 minus nu 2. So H is 6.62 into 10 power minus 34 joule second multiplied with nu 1 minus nu 2. So here it is nu 1 and this one is nu 2. So it is 5.093 multiplied with 10 power 14 minus 5.088 multiplied with 10 power 14. When we solve this one, we will get the value as 3.31 multiplied with 10 power minus 22 joule. So this is how we will solve this question number 50. Now we can move to question number 51. Here the question is the work function for cesium metal is given as 1.9 electron volt. So it is W naught, that is 1.9 electron volt. So this will be given value. Now we have to calculate the threshold wavelength. So threshold wavelength is lambda naught. We have to calculate. We have to calculate the threshold frequency nu naught. Then see if the cesium metal is irradiated with a wavelength of 500 nanometer. We have to calculate the kinetic energy and velocity of excited electron. So these values we have to find. Let us take threshold frequency lambda naught, that is equal to C upon nu naught. So C value is known, 3 into 10 power 8 meter per second, divided by nu naught. Nu naught value is velocity. It is velocity of that is threshold frequency. So first of all we need to find out threshold frequency also. So we know that E is equal to h nu. Similarly W naught threshold work function will be equal to h nu naught. So here we can see we need to find out nu naught. So W naught upon h. So W naught value is given 1.9 electron volt. So 1.9 multiplied with 1.6 into 10 power minus 19. So it will be in this part. Now h value is 6.62 into 10 power minus 34 joule second. When we solve this one, we will get the value as 4.587 multiplied with 10 power 14 second inverse. Now we can use this nu naught, that is frequency, threshold frequency. We can put the value here, 4.587 multiplied with 10 power 14 second inverse. When we solve this one, we will get the value as 654 multiplied with 10 power minus 9 meter. So it will be 654 nanometer. So this will be the value. Now let us find out the kinetic energy of this case, kinetic energy of photoelectron. So kinetic energy of photoelectron is given as the absorbed energy minus the threshold energy. So absorbed energy is hc upon lambda, that is h nu. So hc upon lambda, and threshold energy is work function. So we can find the value 6.62 into 10 power minus 34 joule second, and C value is 3 into 10 power 8 meter per second divided by lambda. Lambda is 500 nanometer, that is 500 multiplied with 10 power minus 9 meter, minus work function is 1.9 into 10 1.6 into 10 power minus 19. When we solve this one, we will get the value as 9.36 multiplied with 10 power minus 20 joule. So this will be the kinetic energy. So that is the second case. We need also to find out the velocity. We can use this formula that kinetic energy is equal to half mv square. So kinetic energy we have got 9.36 into 10 power minus 20 joule equal to half mass of electron is known, 9.10 into 10 power minus 31 kg multiplied with v square. So after solving this one, we will get the value as v as 4.53 into 10 power 5 meter per second. So in this way we will solve this question. Now moving to our next question, that is question number 52. Here the question is, following results are observed when sodium metal is irradiated with different wavelengths. Calculate the threshold wavelength, that is lambda naught, and Planck constant, that is h, as per the given data. So we know that your kinetic energy of the photoelectron is equal to absorbed energy minus threshold energy, that is the work function. So we will put the values here. Absorbed energy means a h nu, so h nu means c upon lambda minus it will be h c upon lambda naught. We can, here kinetic energy is half mv square. Now half mass is, let it be unknown, then velocity v is given somewhat. First case here it is 2.55 multiplied with 10 power 6 uh, whole square, then equal to hc upon here 1 upon lambda, 1 upon 500 minus 1 upon lambda naught. Here it will be 10 power 9 because it is in nanometer, so 10 power 9, 10 power minus 9 will be common. So this is the first equation. Similarly we can write down for the second one also. So it will be half into m multiplied with 4.35 multiplied with 10 power 6 whole power 2 equal to hc upon 10 power minus 9 in bracket 1 upon 450 minus 1 upon lambda naught. Then for the third case it is half m multiplied with 5.20 into 10 power 6 power 2 equal to hc upon 10 power minus 9 in bracket 1 upon 400 minus 1 upon lambda naught. So these three equations are there. Now this is equation 1, this one is equation 2, and this one is equation 3. Now equation 2 divided by equation 1, so it will be equation 2 divided by equation 1. When we put the value, it will be finally we are solving this one, so it will be lambda naught minus 450 upon lambda naught into 450 in bracket multiply with 500 multiply with lambda naught divided by lambda naught minus 500, that is equal to 4.35 divided by 2.55 whole square. On solving this one we will get the value of lambda naught, that is equal to 531 nanometer. So this is the first case. So now putting the value of lambda naught in equation 3, put in equation 3. So by putting this in equation 3 we will get the value, and we will get the h value as 6.65 multiplied with 10 power minus 32 joule second. So this is what the h value, that is the Planck constant, we have got accordingly. Now let us move to question number 53. Here the question number 53 is the ejection of photoelectron from a silver metal in the photoelectric effect experiment can be stopped by applying the voltage of 0.35 volts. When the radiation 256.7 nanometer is used, calculate the work function for silver metal. We need to find out the work function. So here the kinetic energy of photoelectron is given as ev naught, that is v naught means uh, the stopping potential, capital V naught is there, stopping potential, and E is the charge of electron. So kinetic energy will be 1.6 multiplied with 10 power minus 19, that is the charge of electron, multiplied with stopping potential as 0.35 volt. So when it is multiplied it will be 5.6 into 10 power minus 20 joule. So this will be the result. Now absorbed energy by the electron. So the absorbed energy by the electron is given as E equal to h nu. H is multiplied with c. C is nu is c upon lambda. Now h is 6.62 into 10 power minus 34 joule second, and c is multiplied with 3 into 10 power 8 meter per second. Now whole divided by lambda. Lambda value is 256 nanometer means 256.7 into 10 power minus 9 meter. When I solve this one, it will be 7.743 into 10 power minus 19 joule. So that will be the result here. That is the energy we have got, that is the kinetic energy. Now absorbed energy we have found. This one is your absorbed energy. Now your absorbed energy is equal to threshold energy minus that is plus kinetic energy. Absorbed energy is equal to threshold energy plus kinetic energy. Threshold energy is, we can say, it is work function, and this kinetic energy is of photoelectrons. Absorbed energy we have found, that is 7.743 into 10 power minus 19 joule equal to work function, that is W naught, plus kinetic energy is given as we have found 5.6 into 10 power minus 20 joule. Now we can solve this one. We get the W naught value, that is work function, as 7.183 multiplied with 10 power minus 19 joule. Now we can convert into electron volt by dividing with 1.6 charge of electron into 10 power minus 19 coulomb. 7.183 into 10 power minus 19 divided by 1.6 into 10 power minus 19, that is equal to 4.48 electron volt. Now we are with question number 54. Here the question is, if the photon of wavelength 150 picometer strikes an atom and one of its inner bound electron is ejected out of with velocity of 1.5 multiplied with 10 power 7 meter per second. Calculate the energy with which it is bound to the nucleus. So energy of photon is given as h nu. H nu means C upon lambda. So H value is 6.62 into 10 power minus 34 joule second. Multiply with C value is 3 into 10 power 8 meter per second divided by lambda, that is 150 into 10 power minus 12 meter. When it is solved, it will be 1.325 multiplied with 10 power minus 15 joule. Now let us find out the kinetic energy of ejected electron. It will be half mv square. Half multiplied with mass of electron, that is 9.10 into 10 power minus 31 kg. Multiply with velocity, here it is 1.5 into 10 power 7 meter per second whole square. Now when it is solved, it will be 1.0237 multiplied with 10 power minus 16 joule. So that is what the kinetic energy of ejected electron. Now the binding energy of electron to the nucleus, it will be 1.325 multiplied with 10 power minus 15 joule minus 1.0237 multiplied with 10 power minus 16 joule. Now we have to subtract these two values. It is 1.226 into 10 power minus 15 joule. This is the binding energy of electron to the nucleus. We can convert into electron volt by dividing with the charge of electron, that is 1.22226 multiplied with 10 power minus 15 divided by 1.6 into 10 power minus 19. So it will be in electron volt. Divide this value, it will be 7.64 into 10 power 3 electron volt. Let's move to question number 55. Here the question number 55 is that emission transition in the Paschen series end at an orbit of n equal to 3 and start from the orbit n can be represented as given as here, that is v equal to 3.29 multiply with 10 power 15 hertz in bracket 1 upon 3 square minus 1 upon n square. Calculate the value of n. Here we have to calculate the value of n if the transition is observed at wavelength 1285 nanometer. Find the region of the spectrum. We have to find the region of spectrum. Knew that we know frequency is equal to c upon lambda. So this represents small v, it is frequency. Now we have to put this value of nu as c upon lambda. So c value is 3 into 10 power 8 meter per second. Lambda value is wavelength, that is 1285 nanometer, that is 10 power minus 9 meter, equal to 3.29 multiply with 10 power 15 in bracket 1 upon 3 square minus 1 upon n square. So when we solve this equation, we will get n value as 5. So radiation corresponding from n is equal to 5 to n equal to 3 will lie in the which region? It lie in the infrared region, that is your Paschen series. Let's have to the next question. We are with question number 56. Question 56 is that calculate the wavelength of emission transition if it starts from the orbit having radius 1.3225 nanometer and ends at 211.6 picometer. Name the series. We have to identify the series to which this transition belongs and the region of the spectrum. So we know that r value, that is the radius of the orbit in which the electron is present, is given as r equal to n square upon z multiply with 0.529 angstrom. So r value is 1.3225 is equal to n square. So it will be here, it will be n2 square divided by z multiply with 0.529 angstrom. Now another only 211.6 picometer, so it will be now equal to n1 square upon z multiply with 0.529 angstrom. Now n2 is higher orbit and n1 is lower orbit. Now dividing, this one is equation 1, this one is equation 2. So divide equation 1 by equation 2. So finally we will get as n2 square upon n1 square equal to 6.25. Now it will be n2 upon n1, that is equal to 2.5. So therefore we will get as n2 as 5 and n1 as 2. Now we know that your Rydberg equation 1 upon lambda is equal to r z square in bracket 1 upon n1 square minus 1 upon n2 square. So put the values. R value is 1.097 multiply with 10 power 7. Then z value I have taken 1 square 1 upon 2 square minus 1 upon 5 square. After solving this one, we will get the lambda value as 434 multiply with 10 power minus 9 meter, that is 434 nanometer. So this particular wavelength lie in the visible region. So here the region is visible region. Going for question number 57. dual behavior of matter proposed by de Broglie led to the discovery of electron microscope, often used for the highly magnified image of biological molecules and other types of materials. If the velocity of the electron in this microscope is 1.6 multiplied with 10 power 6 meter per second, calculate the de Broglie wavelength associated with this electron. So de Broglie wavelength is given as lambda, that is equal to h upon mv. H is Planck constant 6.62 into 10 power minus 34 joule second divided by mass of electron, that is 9.10 into 10 power minus 31 kg. Now multiply with velocity 1.6 into 10 power 6 meter per second. Now when we solve this one, it will be 455 multiply with 10 power minus 12 meter. Now it will be 455 picometer. That is the de Broglie wavelength. Moving to question number 58. The question 58 is similar to electron diffraction. A neutron diffraction microscope is also used for the determination of structure of molecule. If the wavelength used here is 800 picometer, that is 800 picometer, calculate the characteristic velocity associated with neutron. So here de Broglie wavelength is given as lambda is equal to h upon mv. So we need to find out v. So v will be equal to h upon m lambda. H is given as 6.62 into 10 power minus 34 joule second divided by mass of neutron will be 1.675 into 10 power minus 27 kg multiplied with lambda, that is 800 picometer. So it will be 800 multiplied with 10 power minus 12 meter. Now when we solve this one, we will get as 494.47 meter per second. So this will be the velocity. Moving to question number 59. Here the question 59 is, if the velocity of electron in Bohr first orbit is 2 point velocity is given as 2.19 into 10 power 6 meter per second. Calculate the de Broglie wavelength associated with it. So here lambda is equal to h upon mv. Now h value is given as 6.62 into 10 power minus 34 joule second divided by mass of electron 9.10 into 10 power minus 31 kg. Now velocity is given as 2.19 into 10 power 6 meter per second. Now when we solve this one, it will be 3.324 multiplied with 10 power minus 10 meter. So in this way we will find this question. Now we are with question number 60. Question number 60 is the velocity associated with protons moving with a potential difference of 1000 volt. So here potential difference of 1000 volt is given. Potential difference is this much. So velocity is given as 4.37 multiplied with 10 power 5 meter per second. If a hockey ball of mass 0.1 kg is moving with this velocity, calculate the wavelength associated with this velocity. So we will use de Broglie wavelength lambda equal to h upon mv. We need to find out the velocity. So velocity will be equal to as we need to find out lambda. So h will be 6.62 multiplied with 10 power minus 34 joule second divided by mass of electron, mass of the ball is 0.1 kg multiplied with velocity, that is 4.37 multiplied with 10 power 5 meter per second. Now 1.516 multiplied with 10 power minus 38 meter. So that will be the wavelength. Question number 61 now. If the position of electron is measured with an accuracy of plus minus 0.002 nanometer, calculate the uncertainty in momentum, that is delta P we have to calculate, of the electron. Suppose the momentum of the electron, that is P, is momentum of the electron is given as h upon 4 pi multiplied with 0.05 nanometer. Now, is there any problem in defining this value? So the accuracy part, position of an electron is measured with an accuracy of plus minus 0.02 nanometer. It means uncertainty in position is given as 0.002 nanometer. So it will be 2 multiplied with 10 power minus 12 meter. Now uncertainty in momentum, delta P is equal to h upon 4 pi delta x. So we have to put the values. H value is 6.62 into 10 power minus 34 joule second divided by 4 multiplied by value 3.14, and delta x value is 2 into 10 power minus 12. So this delta x value is given here, we have to put there. When we solve this one, it will be 2.638 multiplied with 10 power minus 23 kg meter per second. Now momentum of electron we need to find out, as it is given h upon 4 pi into 0.05 nanometer. So we have to solve this one. H value is 6.62 into 10 power minus 34 joule second divided by 4 into 3.14 into 0.05, that is multiplied with 10 power minus 12 meter. When we solve this one, it will be 1.055 into 10 power minus 24 kg meter per second. Now we can see here that we have to compare these values. Actual value of momentum is less than the uncertainty in momentum. So this is actual value is a little less. This is actual value which is less than the uncertainty in momentum. Now we are with question number 62. Quantum numbers of 6 electrons are given below. Arrange them in increasing order of their energies. If any of these combination has or have the same energy, list them. So we can see here that energy of electron depends upon your principal quantum number and your azimuthal quantum number. So greater the value of n plus l, greater the n plus l value, more the energy of electron. So let us take the first one. Here we can see n value is 4 and l value is 2. So your n plus l value is 6. Now in the second case we can see n value 3, l value is 5. So n plus l value is 5. Now in the third one, 4 plus 1, that is 5 again, both are same. Now 3 plus 2, 5, again it is 5, both are, the third one is same. 3 plus 1, 4, then 4 plus 1, 5. Now we can see the increasing order of energies will be as per this numbers 5, then lower, then 2 is equal to 4, then 3, then equal to 6, then it will be 1. So this will be the increasing order. Now we are with question number 63. So let us solve this question. Here the question is, the bromine atom possesses 35 electrons. If it contains 6 electrons in 2p orbital, 6 electrons in 3p orbital, and 5 electrons in 4p orbital, which of these electrons experiences lowest effective nuclear charge? Lowest effective nuclear charge is experienced by which of these electrons. So here you will see that the electron farthest from the nucleus. So this is the nucleus, first shell, second shell, third shell, fourth shell, fifth shell. So whatever the electron which is farthest from nucleus will experience lowest effective nuclear charge. So here you will see it will be your 4p electrons which will experience lowest effective nuclear charge. Now moving to question number 64. Among the following pairs of orbitals, which orbital will experience the larger effective nuclear charge? So A, whether it is 2s or your 3s orbital, which will experience larger effective nuclear charge. So the point is that closer to the nucleus, or closer is the orbital to the nucleus. So the closer the orbital to the nucleus, larger will be the effective nuclear charge. Larger will be the effective nuclear charge. So here we will see your 2s orbital will experience larger effective nuclear charge because this orbital is more nearer to the nucleus. B part, it is 4d and 4f. So here we will see that 4d orbital is more near to the nucleus, so it will experiences larger effective nuclear charge. Experiences larger effective nuclear charge. C, we have 3d and 3p orbital. So in this one we will see that your 3p orbital is more near to the nucleus, so it will experience a larger effective nuclear charge. The main point is that the orbital which is more near to the nucleus will experience more effective nuclear charge. Moving to question number 65. The unpaired electrons in aluminium and in silicon are present in 3p orbitals. Unpaired electrons. Which electron will experience more effective nuclear charge? So which electron will be there which will experience more effective nuclear charge? So here aluminum atomic number is 13 and silicon atomic number is 14. We can calculate the effective nuclear charge as Z star equal to Z minus sigma. So due to greater nuclear charge, that is Z value, the 3p electron of silicon will experience more effective nuclear charge, as we can see here that it will be having 14 electrons. So 3p electron of silicon will experiences more effective nuclear charge. Going to question number 66. Indicate the number of unpaired electrons. Number of unpaired electrons we have to indicate. So first one is phosphorus having atomic number 15. Let's write on the configuration: 1s2, 2s2, 2p6, 3s2, 3px1, 3py1 and 3pz1. So these p orbitals are not completely filled, so it will be having 3 unpaired electrons. 3 unpaired electrons are there in 3p orbital. Second one, we have silicon having atomic number 14. Its configuration is 1s2, 2s2, 2p6, 3s2, 3px1, 3py1. So here these three here it is 3p orbital, 2p 3p orbitals are incompletely filled, so having 2 unpaired electrons. Going to third one, that is chromium. Chromium atomic number is 24. Its configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d 3d6. It will be 3d 5, 4s1. So here we can see one, we can see here it is 3d6, 4s1. So having 4 unpaired electron here and 1 unpaired electron in this, overall 6 unpaired electrons are there in 3d and 4s. So 6 unpaired electrons are present. Fourth one, we have iron. Iron atomic number is 26. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. 4 unpaired electrons present in 3d orbital. 4 unpaired electrons are present in your 3d orbital. Fifth one, we have krypton, that is atomic number 36. So it will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6. So here it will be all orbitals are completely filled, so it is having 0 unpaired electrons. It is an inert gas. Moving to question number 67. Here the question is A. How many subshells are associated with n equal to 4? Principal quantum number is given as 4. So how many subshells are there? So L value will be 0 to n minus 1. So 0 to 4 minus 1, 0 to 3, 0, 1, 2 and 3. That is S, P, D and F. So these subshells will be there. So it will be 4s, 4p, 4d and 4f. These subshells will be associated with this principal quantum number 4. B part, how many electrons are present in the subshell having spin quantum number as minus half and n value is equal to 4. So if you want to find out for n equal to 4, we need to find out how many number of electrons. It is given by 2n square. So 2 multiplied with 4 square, that is 16, 16 to 32 electrons are there. Now we can see here spin quantum number anti-clockwise is shown. So it will be half of 32, that is 16 electrons are associated with this case when n equal to 4 and your anti-clockwise direction representation is there. That is half will be anti-clockwise spin and half will be clockwise spin. So 16 electrons will be the answer. So in this way we have come across these questions. Hopefully maximum students should go through these question and answers for this chapter, structure of an atom. We have gone through all these questions of in-text also and your exercise question also. Hopefully you will able to understand, and let's have other chapters also in coming days.